Chi-Squared test, the test for goodness of fit for categorical data. First of all, what is a Chi-Squared test? Well, a Chi-Squared test is a type of test where you can test patterns and similarities between various sets of categorical data without having to perform multiple tests like you would if you were doing a significance test for proportions, right? There's three different versions of a Chi-Squared test. The first one is a goodness of fit, which can be used to determine whether or not a hypothesized distribution matches up with what you have observed. There's the Chi-Squared test for homogeneity, which can be used to determine whether or not a categorical variable differs between two or more populations. And then there's a third version, which is a test for independence. It can be used to determine whether or not there is an association between two different categorical variables. So when would you use a Chi-Squared goodness of fit test? Well, let's look at the following scenario. Suppose Mars Candy Company says that the proportion of blue M&Ms in their candies is 0.24. You get a bag of M&Ms that has 9 blue ones out of a total of 60. Since 9 out of 60 is only 0.15, you decide you're going to test their claim. You could do this using a significance test for proportions, where your null hypothesis would be that the proportion of blue M&Ms equals 0.24, versus an alternative where the proportion of blue M&Ms does not equal 0.24, and you could go out and test this for blue M&Ms. You could do this theoretically for each of the 6 different colors of blue M&Ms, and you could compare each test and each result to see what the likelihood that they follow their described pattern as told by Mars Candy Company. But that involves having to do 6 different tests, 6 different significance tests with 6 different sets of hypotheses, and who really wants to do that? So instead, we can use what's called a Chi-Squared test. In order to perform this test, we would need to know the counts for the variables that we're talking about. The observed count would be how many of each color M&M we actually had in our possession, or in each bag. And then the expected counts is how many of each color of M&M we are told are made overall. Now, the further away our observed counts are from the expected counts, the more evidence we have against the null hypothesis. The null hypothesis in this case being that the proportions of M&Ms are what they say they are. So assuming the company isn't lying, we should expect 14.4 blue M&Ms in our bag. You could go through and complete this for all the different colors, and you might get a table that looks like this. You see you have the observed counts for each of the different colors of M&Ms and the proportions compared to what Mars Candy Company says they should be in a bag of 60 M&Ms, right? Now, the Chi-Squared statistic is a measure of how far the observed counts are from the expected counts, and the formula is as follows. So you take the observed value, you subtract the expected value, you square it, and then you divide by the expected value again. And then you add them all up. So in this situation, if we use this statistic, this would be what it would look like. You have the 9 minus the 14.4 squared divided by 14.4 for the blue ones. You have the same for all the various different colors. And you would add each of these up to get a total of 10.18. You can look at this kind of like a measure of how far away the total amount is from what should be expected, right? So large values suggest that the observed amount differs very much so from what was expected, whereas small amounts kind of suggest that it's right on where it should be, right? Also, large amounts for Chi-Squared suggest the alternative hypothesis, whereas small values suggest the null hypothesis, which makes sense. The further away something is from what is expected, the less likely it is we get what we're expecting. Now, of course, each test has its own set of conditions. Thankfully, the conditions for these are pretty straightforward. Is it random? Do you have less than 10% of the overall population? And does each category have at least 5 in it, right? So when we look at this table, we can assume that the M&Ms are randomly selected. We know that 60 is less than 10% of all the M&Ms in the world, And we see here that we have at least 5 observed counts for each different category here. So yes, our conditions are met. And that would be all we would have to check. Once you have your chi-squared statistic, you need to then find your degrees of freedom. Now, before we learned degrees of freedom was n minus 1. For chi-squared tests, it's number of rows minus 1. So for us, we have 6 rows, so our degrees of freedom would be 5. So our chi-squared statistic for this scenario is 10.18 with 5 degrees of freedom. So we can then go to a chi-squared table and find 10.18 with 5 degrees of freedom, and that would give us a p-value somewhere between 0.1 and 0.05. So then we compare that to, our standard 0.05. 0.1 and 0.05 are, well, a number that is between 0.1 and 0.05, we would expect greater than 0.05. So for this, we would fail to reject the null hypothesis. Now you may say to yourself, well, 10.18 is kind of a big statistic. Yeah, I know, but the thing is with tests like this, it's a different curve from the normal curve, so it follows a different set of rules, and sometimes you need that chi-squared statistic to be really big in order to get a p-value that's less than 0.05. So in this case, we would reject the null hypothesis. Right? Now, what does that mean in context for the M&Ms? Well, what that means is that even though our observed values differ from what we should expect by a pretty decent margin, who likes yellow M&M? In reality, it's not so far enough away that we should consider it exceptionally unusual, right? We don't have enough evidence here to say that the Mars Candy Company that produces M&Ms is lying to us, right? It's close because the p-value is between 0.1 and 0.05. When you run it through the calculator, you get 0.07, so it's close to being at that 0.05 threshold. It's just not quite there. But yeah, that's essentially how chi-squared statistics works. Stay tuned for the next video to see an example of how to do it on the calculator.